Good morning, dear students. Myself Karthik Pandya. Today we will talk about the power system optimization via computational intelligence method. We will try to solve the optimization problem of the power system using computational intelligence method or artificial intelligence method. You must have observed that in the last 10 years, the application of artificial intelligence methods or computational intelligence methods has increased drastically, and more research is being carried out to increase the usage of artificial intelligence methods. So today we will see the application of most powerful and very good, excellent optimization method, that is a particle sum optimization method, to minimize the losses of the power system. So this is the outline of my presentation. First of all, we will see the definition of the optimal reactive power dispatch, which is also called as the loss minimization problem in the transmission power system. And then we will see the sources of reactive powers. Then we will study the particle sum optimization method in detail. Then we will see the mathematical modeling of the state changing transformers. Then problem formulation. We will see the test 41 bus test systems. Then we will see the conclusions and discussions. Now we will see this definition of optimization later on. We will solve a very simple sum. So what is the optimization? The main aim of optimization is to find the best solution among many possible solutions available while satisfying the various types of equations, which are known as the constraint equations or restriction equations. I have listed out some applications of optimizations. I have listed only 5 to 7 applications, but there are ample number of applications of optimization in real world in every engineering discipline. Right. So based in as far as the medical science is concerned, CT scan machine is using optimization. Then in your mobile phone, the dynamic programming is continuously run to optimize its resources. Then in stock market, the pricing of the stocks are determined using a linear programming method, which is the optimization method. Then in aviation system, the routing of the various aeroplanes are decided by the nonlinear programming. Then in power system, there are ample applications of optimization in power system, then protection, power electronics, and so on. So actually, the working principle of optimization is very old. It has been used since last 17 to 80 years. But as far as the electrical engineering is concerned, in 1968, Professor Domel and Professor Tini proposed the actual use of optimization into the power flow, into the power system, and is a excellent paper, that is optimal power flow solutions, which was published in IEEE Transaction on Power Apparatus and System in 1968. And that paper was the fifth most important paper in the 20th century power system analysis. It was the high impact factors on power engineering from 1900 to 1999. So Professor Tini is also known as the father of the modern computer solutions for electrical power network, as per the IEEE PES magazine article published. So the theory which you see in power system, the most of the theory are based upon the paper published by Professor Tini in 1968. Now, as far as the power system is concerned, optimization used in optimal power flow, in state estimation, in stability analysis, fault analysis, security dispatch, congestion analysis, pricing, etc. So now, after having known this fact, we will try to study the working principle of best optimization method, that is particle sum optimization. And I will start from the very basic mathematics, and gradually we will see the detailed mathematics of PSO. So, as a basic rule, if you consider any engineering problem, then the any engineering system is shown by their mathematical models, and mathematical models consist of number of equations. You consider any engineering system, ultimately it is nothing but the number of equations, and our aim is to solve this number of equations simultaneously. We want to obtain the solutions of the equations. This is our aim, and there are number of methods available, and many methods we have studied in engineering as well as in 12th standard, right? So let us start from the very basic. Suppose I have one equation, that is, I would say x square is equal to 100. So what is the solution of this equation? X is equal to plus or minus 10. This is a very simple system. This system consists of only one variable, and this system also consists of only one equation, right? So when uh, for this system we get the unique answer, unique solution, that is x is equal to plus or minus 10. We have got the unique solution, right? I would also generalize this fact. I would consider variable as n. So I write n is equal to number of variables, and for equations I would call m. So m means number of equations, right? In most of the books, n is used for the number of variables and m is used for the number of equations. So now in this case, now let us proceed further. Let us consider the another case. Now I consider the two equations. Very simple two equations. Suppose I say x plus 2y is equal to 80, and second equation is minus 3x plus 8y is equal to 100. Now this system consists of how many equations? Two equations, that is n is equal to 2. And how many variables are there? There are two variables, x and y. So there are two variables. So m is equal to 2. and n is also equal to 2, right? And in lower standards we have seen such type of equations, right? We can solve these equations. Suppose I multiply this, I want to remove this x, so I will multiply this equation by 3. So 3x plus 6y is equal to 240 minus 3x plus 8y is equal to 100. So ultimately you will get the answer of x and answer of y. You will get the unique values of x and y, right? So in this case also, mathematically I would write n is equal to m, right? N is 2, m is 2. So I get the unique answer. I get the unique solution. Clear? So from this we will define one rule: when number of variables are equal to number of equations, we obtain the unique solution. We obtain the unique solutions of variables, right? And in load flow analysis you must have used the Newton-Raphson method, right? In Newton-Raphson method the number of equations and number of variables are made same, and then you get the unique solution. So right now in the same part I would increase some of the complexities. So see the last sum, I consider another sum. Now suppose this is the equation: 2x plus 3y is equal to 8 minus 3x plus 4y is equal to 7. Now I add another equations as well. So suppose I write like minus 4x plus 7y is equal to 10 minus 8x minus 8y is equal to 12. Now tell me what is the difference between this case and the previous case. Now in this case, how many variables are there? There are two variables. So n is equal to 2, right? Number of variables are 2. Now how many equations are there? Now there are 1, 2, 3 and 4. There are 4 equations, so m is equal to 4. Equations are m is equal to 4, right? Now in such case, if you now what happens in this case, number of equations are more than number of variables. Number of equations are more than number of variables. So if you solve these 4 equations simultaneously, then you will obtain the multiple solutions of x and y. You will get multiple answers of x and y, right? You will get multiple pairs of x and y. So now our aim is to get the best answer. There are multiple answers and we have to find out the best answer which will optimize a specific function, which will optimize the specific specific function, and generally we consider as that function as a cost function. It may have the different name also, right? So this process of finding the best solution among the possible solutions, multiple possible solutions, this word is important, possible solutions multiple possible solutions while optimizing a specific cost function. Either we want to minimize a function or we want to maximize a function, and this procedure is called as the optimization, right? So again, I repeat this definition and this concept. So optimization is a process of finding the best solutions among multiple possible solutions with the aim to minimize or maximize a specific objective function while satisfying the constraints, while satisfying these constraint equations. It means your obtained answer x and y, this is x and y, this is x and y, should be such that it should simultaneously satisfy all these constraint equations. This is the basic requirement of optimization. Your optimum answer, your best answer should perfectly satisfy each and every constraint equation, right? Suppose, let us say I obtain x as 0 and y as 0. So this is my possible solution. This is my possible solution. Now I want to find whether this is the optimum answer or not. So as I told earlier, this possible answer should satisfy each and every constraint. So in this equation 1, replace x by 0 and y by 0. So ultimately you will obtain you will you will obtain x 2 into 0 plus 3 into 0, so it is 0. So LHS obtained is 0, but RHS is 8. So LHS is not equal to RHS. It means this solution 0 0 does not satisfy equation number 1. This solution does not satisfy constraint equation number 1. So this x y 0 0 is not a solution, even though it is a feasible answer. It is not the optimum answer. Why? Because it does not satisfy, in this case, first constraint. In generalized form, if the optimum answer does not satisfy at least one constraint, then it is not an optimum point. So your optimized values, your optimized answer should simultaneously satisfies all the constraint equations. It means if you replace x by the obtained value and if you replace y by the obtained value, then you should get LHS exactly equal to RHS, exactly equal to RHS in this case. In this case, I have used the equality, so this is known as the equality constraints. This is known as the equality constraints. There are other types of constraints also, which are known as the inequality constraints. We will see it later on. Okay, so see the second slide. This slide, our aim was to find out the solutions of the equations, right? And in that case, n is equal to m, so we obtain the unique solutions. But in this third slide, in this case, the m is greater than n, right? So our what is next conclusion? The conclusion is when the number of equations when the number of equations, that is m, is greater than number of variables, that is n, You will obtain the multiple solutions, and out of those multiple solutions you have to find out the best solution, and this procedure is nothing but the optimization procedure. So when you study any problem in your BTech or MTech or PhD study, and if you realize that the number of equations of your models are more than the number of variables, then you have to formulate that problem as the optimization problem, and you have to use the optimization method to solve your problem. Now you may ask, I don't want to use the optimization for this case, right? If number of equations are more than number of variables, still I don't want to use optimization. Yes, you can use the other methods, but you will not get the optimum answers. Suppose you want to minimize cost of your simulation project, or you want to minimize the cost of any plant or you want to minimize the cost, operational cost of the system, running cost of the system, then you have to use optimization. There is no other way. If you don't use the optimization, then you will not optimize that system, you will not minimize the cost. This is the problem, right? So in the research work also, yeah, you can formulate any system, and based upon your system you can define your variables, and you can formulate the constant equations. Yes, you have to formulate the equations and variables, and if you find this case, then you have to consider the optimizations, and you have to use the optimization algorithms, right? Okay, so this is all about the basic of the optimization. Now as I told earlier, there are the history of optimization is very old. Since last many 17 to 80 years, various optimization methods have been proposed by the various scientists. So broadly speaking, the optimization methods can be classified into two types. Are classified into two parts. First part is the classical optimization methods, and second part is the artificial intelligence or computational intelligence or meta heuristic optimization methods. They are also called as the nature inspired nature inspired meta heuristic methods. Meta heuristic methods. These meta heuristic methods are also known as the stochastic methods. Stochastic methods. Sometimes these stochastic methods are also known as the probabilistic methods. Some authors use that word also. So, probabilistic methods. See, every year, one special conference, that is PMA, PSO, uh, probabilistic method applications in power system, PMAPS, is organized every year. This conference is only dedicated to the research which is carried out in probabilistic methods. And ultimately, probabilistic methods are mainly based upon the computational intelligence based method or AI based method. So this is the broad category of the optimization methods. Now, classical methods, they are also very good methods. Some of the classical methods are the steepest descent methods, descent method, then Newton's method. Remember the Newton-Raphson method which you study in load flow analysis and this Newton's method, both are different. This is the Newton's method of optimization, right? Then conjugate gradient method, this is another classical method. Then interior point method, etc. In AI method, there is a vast list. I list some of the popular methods, that is a particle swarm optimization method, then a cuckoo search optimization method. This cuckoo search method has been inspired from the behavior of the cuckoo quail who lays their eggs in the nest of the other birds. From its behavior, the algorithm has been proposed by Professor X. S. Young of Cambridge University. Then the differential evolutionary algorithm, DE algorithm. Then there is another method which is the covariance metric adaptation evolutionary strategy, CMES algorithms, right? So there are number of AI methods and number of classical methods, right? All methods are very good methods, right? Okay, so in today's session we will study the particle swarm optimization method. Okay, I will start from the basic mathematics of optimization, right? Suppose I have this graph x, and here it is f of x. F of x is equal to y. Function of x, this is equal to y. This is a quadratic function, right? This quadratic function will have the term like x square plus 7x plus some constant c, right? I have not exactly written the equation, and this graph is not drawn as per the scale, right? But this is the quadratic graph. Now I want to find the point at which this function gets minimized. The function value will become minimum. It means y value will become minimum. We want to find out x such that f of x, that is equal to y, will become minimum. This is our aim. And yes, when you want to minimize, sorry, when you want to minimize or maximize a specific function, this procedure is called as the optimization. So can you locate the point at which this function becomes minimum? Right. So yes, at this point, this x, at this x function becomes minimum. This y is minimum. So for any other x, right, this x, the function value y will be higher than this function value, right? So this is the minimum value. See, for x, this x, This is the function value. This is obviously higher than this value. Okay. So this x is the best answer for our optimization problem. So as per the rule, this best answer is designated as x star. So this is the optimum answer, optimum solution, optimum solution. It is designated as x star. And corresponding to x star, the function value corresponding to x star, f of x star, it means suppose I get x is equal to 5 in this case, then in this equation f of x, replace x by 5, right, and c is known, replace x by 5, so you will get some value of f of x, some value of f of x. Suppose I get the value of f of x is 10, right, this vertical distance of y or f of x. So this vertical distance 10, it is the optimum function value, optimum function value or optimized function value. This is also called as optimized function value, or it is also called as minimized function value, minimized function value. In this case we minimized the function, so it is a minimized function value. So yes, this is the very basic of optimization. What we do in optimization, we do nothing, but we find x value, we find the value of the variable x such that it will minimize the objective function, right? And yes, as per the rule, this variable x have number of synonyms. This x is called as the variable. This x is also called as the control variable. This x is also called as the decision variable. This x is also called as the state variable. X is also called as the optimization variables. Optimization variables. So, right, so 1 2 3 4 up to 6, so there are 6 synonyms, right? So most of the books use this word decision variable or state variable. In power system we use the word state variable or optimization variables, right? So any optimization problem consists of number of control variables or optimization variables, and our aim is to find the best values of the optimization variables which will minimize the objective function. So our aim is to find out x star, and corresponding to x star we will find out f of x star, f of x star, f of x star. This is our procedure. And yes, this function is called as the objective function. Function is called as the objective function. It is also called as the fitness function. Yes, in genetic algorithm or in any artificial intelligence method, this word is generally used, fitness function or objective function, right? Or cost functions. There are lots of names depending upon the type of function. The name is given cost function. In a restructured power system, we use the term social welfare optimization. Social welfare optimization cost function, right? Then also we yes, there are lots of fitness functions, right? Then maximize the total transfer capability capability of the transmission lines, etc. Right? Okay. Now we will start studying the most powerful optimization uh, computational intelligent optimization method, which is known as the particle swarm optimization method, which is in short known as the uh, PSO. Truly speaking, we all know the working principle of particle sum optimization. Everybody knows this algorithm, but uh, the unknown facts is we don't know its mathematical equations, right? Now I said earlier, you know the particle swarm optimization. Now let us consider the real example of the birds which are flying in the evening hours, to find the food, right? And yes, you must have observed the specific patterns of the birds which fly during the evening hours, right? So yes, you must have observed this pattern. This is the bird fly in a group, and typically you must have observed such type of a wheat shape pattern, right? These are the birds, these are the group of birds, and this group of birds are known as the swarm. Group of birds is known as the swarm. So all these birds fly in a group to find out the food source, right? So what are our observations? So at present I am taking the example from the nature, and after concluding 2 to 3 facts, we will gradually see the mathematical equations of PSO, right? See, remember, optimization or rather engineering is all about mathematical equations, nothing new. All are based upon the mathematical equations. Okay, yes, right now, what are our observations? Our observation is all birds, all birds fly in a group. Now, second observation, you must have observed that there is a group leader which is ahead of remaining birds, right? There is a group leader. There is a group leader. There is a group leader ahead of the remaining birds, right? And what is our third observation? Every bird, I also called it this bird as a particle, right? Every particle or every particle will follow this leader. This leader. You must have observed this fact. If this leader changes his direction or velocity, then the remaining birds also change their direction as well as velocity, right? So our conclusion is every bird follows the group leader. Everyone will follow the group leader, right? Why every bird follows the group leader because this leader is very near to the food source. We are assuming this fact, right? Okay. Also, so this third term, every bird follows the group leader. Now we will try to see in terms of mathematics. It means every bird, suppose I take this bird and this bird, every bird will try to minimize the distance between its current position, this position, and the position of the group leader. Position of the group leader. It tries to minimize this distance. In terms of mathematics, we can conclude like this, right? Okay. Also, every bird, every two birds, every neighboring birds will try to minimize the distance between them, right? Okay. So these are our observations, and from these observations, in the year 1995, Professor Kennedy and Albert of Australia proposed this particle swarm optimization algorithm in the conference paper. And from that year, the PSO became very popular, and lots of research had been carried out since last 25 years. A number of papers have been published, and lots of research work had been carried out. So, having known these facts, in the second lecture, we will try to formulate the equations of PSO, and then we will formulate the objective function of the loss minimization, and then we will try to solve the loss minimization problem using the PSO method. Thank you.